Hello to everybody and welcome to another exciting week of KETIV Virtual Academy. My name is Tyler Hart and today we will be discussing Ansys Mechanical Parametric Design, the simulation solution. Your expert today will be Joel Bay, an application engineer for Ansys Mechanical here at KETIV. And we're looking forward to hearing from Joel today. A couple quick housekeeping items. As usual, please feel free to send questions to the Q&A, not to the chat. And we'll do our best to get those answered either during the session or at the end. Also, all of these sessions are recorded and available for distribution on ketiv.com or on our YouTube channel. So feel free to share those with your peers as you see fit. So without further ado, I'll just pass it right on over to Joel to get us started. Thanks so much for being here, Joel.
Yeah, thanks a lot. Thanks for the introduction, Tyler. Yeah, so I'll go into a little bit further detail about myself. So yeah, like Tyler mentioned, my name is Joel Bay, application engineer at KETIV. I've been here for a better part of a year now. Ansys certified application engineer for mechanical application. Got a master's degree in mechanical engineering and about 4 years of experience in structural analysis and design. So kind of before we go into the what and how for these Ansys parameters, I want to talk a little bit about the why. And I mean, maybe the why is intuitive, right? But when we use parameters in our analysis, it helps us answer a couple questions. And most importantly, it helps us quantify the design space, which is really important in kind of the immature stages of the design process, right? When I change X variable, what does it mean for my results? Like, for instance, maybe I have a thickness of a component and I can vary it and I can see how does it actually affect whatever stress is in that area. That's a particularly obvious example, but it's not always that obvious, right? There's obviously there's many parameters that exist that you can vary, or many specs of a component that you can vary, and the actual change on the system is not going to be obvious without doing any kind of analysis work. One example of that is like a wind turbine blade in the bottom right. I worked in wind turbine blade design for a few years, and one of the things that we were always trying to do is quantify this design space. And one of the ways we do that is by changing the thickness of the material that constitutes the blade, the fiberglass, right? And seeing how that changes the global stiffness of the blade, right? Like how much it deflects at the tip, for instance, if you were to change the thickness of the main spar beam throughout the length of the blade. But also when we work with parameters, it gives us some confidence in our design decisions, right? I mean, analysis does that as a baseline, right? Because once you've done some analysis on something, you're going to gain some confidence as a baseline. But once you start working with parameters, you can go through many different iterations and really be sure that you're making the right decision about your design. And then lastly, it helps us to optimize designs. Of course, we have other tools just for optimization. And with one example of that is OptiSling. You may have heard of that. I won't be talking about that here. I'll just be talking about Workbench parameters. But we have tools for just strictly for optimization. But you can approach optimization using Workbench parameters, and it's really easy to do, and I'm excited to talk about that today. So let's talk about the exercise that we're going to do, and that's this T-pipe here. So it's a really simple component, right? And we're going to be pretending that we've been tasked with specifying a wall thickness for the pipe and also to choose its material. And we're going to have some considerations for that. I see there's a message in the chat. That was just me, Joel. Just you. Okay, thanks. Some considerations. We'll have a fluid flowing through the pipe. It's less than or equal 150 degrees Fahrenheit. It's going to be pressurized at 100 psi. And it's also going to support a load. It's going to have a support on the left side of the pipe, and it's going to have some kind of pipe assembly to the right of it that exerts a load 450 pounds downwards. So we're going to say it's in this direction. And it's going to be acting 1 foot from the right face of the pipe. So, very interesting and plausible situation that we could have here. And I'm going to show you how to set it up and also how to parameterize it and how to make it easy to make a design decision. But to make that design decision, we're going to have some options, right? Right now we've got, we have the wall thickness and the material as options, but we need maybe one more criteria for that. And so I've made up this this table of a bunch of different pipe options. You might imagine that you have a pipe vendor, and they have 4 materials that you can choose from, and they have all these different thicknesses that you can choose from for the pipes too. So now we've got a price associated with all of them. As our cheapest material, where we have this aluminum at $5 for this thinnest pipe, 1/16 of an inch, and we have structural steel as the most expensive material. And then our pipes go all the way up to 1/2 an inch in thickness. So yeah, it'll be a little bit more interesting. We'll now assess all of these pipes and just choose the cheapest one that meets our design requirements, which were listed out up here. So now I'm just going to go into the demo. So how do we do this in Ansys, right? How do we make this kind of design decision? Well, we're going to start by opening up Workbench as always, and we're going to add some analyses. So which ones are we going to add? Well, what are our design considerations? Well, we have a thermal condition because we have this this fluid running through the pipe at 150 degrees Fahrenheit, and we also have some loads that are being applied. So we have some pressure, and we have this this 450-pound assembly acting on the pipe. So we're going to go ahead and add a steady state thermal and a static structural analysis. And to do that, we just drag and drop them into this white space here. And we're going to link the static structural analysis to the solution branch of the thermal analysis. So what all that's saying is, we might want to consider some thermal stresses here. So we're going to go ahead and link that static structural to the solution branch of the thermal, because that lets us look at the temperature distribution from the thermal analysis and calculate those thermal stresses. All right. So now that we've done that, we're actually going to just import a geometry that we've already made of the pipe. And to do that, we just import this geometry like this, so. And after that, what we want to do is I have some geometry parameters, so we just have to open up that geometry in SpaceClaim real quick, and then it'll populate here in Workbench. And while I'm in SpaceClaim, I'm actually going to show you how to add parameters in SpaceClaim, because that's it's going to be an important part of your parametric analysis, is having some parameters to run. So I only got this one SpaceClaim license, and it's already open, and I just forgot about that. So I'll just open that up here. But I could have opened up just from Workbench, of course. And so when you first open up SpaceClaim, right, you're not going to have your parameters over here. I've already added them in here, and that's why they're over here. But to add parameters, it's really simple, actually. You just modify your part in any way you'd like. For instance, if I wanted to modify this inner diameter of this horizontal pipe here, I could just click on this this inner surface here, and this radius pops up, and it says it's 2 inches, and there's this P next to the radius, and that's actually the button that you're going to click to add as a parameter. So if you'll see, if I click it here, over in the parameter list, this parameter 1 pops up, and it's listed as 2 inches. So that's how you add any kind of parameter that you like. And of course, it can be much more complex than that. For instance, we have this pipe half length here, which I've created as a constraint. And you can actually make it so that you can impose a symmetry condition. And then if I were to edit this length, say to 6 inches, which it should be, then it's actually going to be reflected on the side. Of course, you couldn't see it because it was so close to the original length. But let's go ahead and make it a little bit bigger so you can see that it's reflected on that side. So that's really useful, right? Because it's a fairly complex dimension to include there. I'll go ahead and Control Z that. Now it's back to its original length. And that's kind of the basics of adding parameters in SpaceClaim. I'm not going to go into too much detail on that because I don't want to make the KVA about SpaceClaim. But the gist is if you edit a model with pretty much any kind of operation, for instance, if I were to lengthen it, I'll just show you one more time like this. Rather, first you must click, then pull. This little P pops up, and that's how you add any kind of dimension you'd like as a parameter. So now I'll go ahead and close that. And actually going to go ahead and hop over to this this model on the left here, because I've already done some setup work just to make things easier with the explanation. So now I'll open up the model in Mechanical. And I'm going to start going through our design considerations and making sure they're accounted for in our model here. Apologies. One moment. Okay. Apologies for that. Okay. So now we've got our model open. And first thing that you always want to consider when you're opening up a new model is to make sure that you've got your geometry right and your materials right? And so we know we've got our geometry right. We've looked at our geometry in SpaceClaim. But when I go to our material section here, we only have this structural steel added. But we know from our design considerations in our PowerPoint that we have to consider a few others: carbon steel, aluminum, and copper. So we're going to go ahead and add that in our engineering data tab here. So to add material properties and engineering data, it's very easy. You just go to this engineering data sources, and of course you can add your own. And I won't go into too much detail on that. But I will just add our materials that we need: aluminum alloy, copper, and then we'll go to Granta. And we'll grab carbon steel. First, we'll have to find it. There it is. Okay. So I've just clicked on all those plus signs next to the materials in our material library. And now in our model library, we have all those materials in here. And now when I go to mechanical, I can just update the model, refreshing the materials, and then we'll see that all these material properties have been added. But we want to assess these materials in a parametric fashion, right? We don't want to just continuously edit the material of this solid here. We want to be able to just tell Ansys, okay, run all these different load cases with all these different materials. And how do you do that? Well, it's really simple. within our geometry branch under the solid body, there's this material section here, and you can just click on this white box, and this P appears in the white box, just like in SpaceClaim, right? Just like in SpaceClaim with the white box, if you were to click it, you get this, you parameterize that particular number or material. It's the same case here. So now we can edit that this material as a parameter, just like that. Okay, so that's our first design consideration, right? That we have to consider those 4 materials. The next one is that the connector will have a hot fluid running through it at 150 degrees Fahrenheit. And so how are we going to simulate that? Well, we've got our steady state thermal analysis, and we're going to just add a temperature boundary condition on the inner wall here, and it's going to be at 150 degrees Fahrenheit. So all I have to do is right click on that surface, add a temperature boundary condition, and type in this 150 degrees here. And notice I can also parameterize this temperature as well. So we're not just limited to our materials or our geometry. We can also parameterize the loads. But in our in our design problem, we have this fluid running at a maximum 150 degrees Fahrenheit. So to me, it makes sense to just assess it at its maximum temperature. So we'll just go ahead and do that. And that is that entire consideration. Next, we'll have a support that exists on the horizontal section and the pipe assembly that exerts a load of 450 pounds acting at 1 foot from the right face. So to add this support on the left, right? We don't want to actually model the support. The easiest way to do it would just be to add a fixed support onto this face. But actually, we don't want to do that. We don't want to do that because we have this temperature distribution, or we're going to have a temperature distribution within the pipe, and we want to consider thermal stresses. And when we have a fixed boundary condition on this side of the pipe, we'll get some very high stresses, right? Because you can imagine it, the pipe wants to expand here, or these particular nodes want to expand due to the thermal boundary condition, but they can't because they're fixed. So you'll have to have some compensation at the adjacent nodes, and you'll get some anomaly stresses. So instead of that, we have a solution here, and this is kind of just like a quick tip that isn't necessarily related to parameters, but we can actually put in here a remote displacement. And we're going to, well, what is a remote displacement, first of all? So, well, a fixed boundary condition is a displacement boundary condition, right, of 0. So we're saying, okay, all the nodes on this face are fixed. They can't move. They have a displacement of 0. When we have a remote displacement, instead of directly constraining those nodes, we're actually just constraining this this center node. It's going to be called a pilot node, and all the other nodes that are going to be constrained are just going to be constrained relative to that center node via some kind of stiffness relationship. So you can imagine now, instead of these nodes being fixed, they now try to displace, but there is some kind of stiffness that's resisting their displacement. So we're going to constrain that pilot node to be 0 in all directions. And making the behavior deformable, that means that this face can deform, right? Which is what we want, which is the whole workaround. So that's our support on the left side. And next we want a load to be acting in the downward direction, 1 foot from this face. And it's going to be transferred to this face somehow through some kind of connecting pipe, right? Now, this could be kind of an intimidating question, right? Like, how do I model a load that's acting 1 foot away? I mean, it's going to result in some kind of moment on this face. Do I apply a moment to the face, right? Well, it's actually, the answer to that is a lot easier. All right, so we have this tool in Ansys Mechanical called a remote force. And so, and you notice I had a remote force in here earlier, but what the remote force is, it's very similar to the remote displacement, where you're actually applying this boundary condition not directly to the nodes themselves, but to some pilot node, and then it's translated to those nodes. And so when we have this remote force, we can actually apply this force 1 foot away to some pilot node, and then it will translate that force. It'll transfer that force to those nodes through these constraint equations in a similar way to the remote displacement. So what was our force here? Our force was 450 pounds, and again, it was acting 1 foot from the right face. So all I do here is, instead of defining it by vector, I'm going to define it by components, and it's going to be 450 pounds in the z direction and 0 pounds in either the x or y. But at the moment, it's being applied to the pilot node that's in the middle of this face, which is not what we want, right? It's not what we want. Really, it's 1 foot away. So to make that happen, we can look at our y coordinate here, which is some crazy number. And we're going to put an equal sign at the front because we want to put an equation. And we want to say, well, it's going to be 12 inches away. And I put a negative sign, right? Because it's in the y direction. Now, if I zoom out, you can see that this force is being applied about 1 foot away. And it's in the downward direction. So that is actually set up completely now, this third design consideration. And then lastly, we're going to have an internal pressure on the pipe of 100 psi. So to do that, it's pretty similar, where this is actually very simple to set up and very intuitive. We simply select all the internal surfaces and we add a pressure. And we set it to a magnitude of 100 psi because that's what we have here. All right. And that's really all we have to set up in order to get our solution results. So let's go ahead and do that. I've run this model before, so I know it runs very quickly. So first we're running this say thermal analysis just to get this temperature distribution, right? And we can look at that temperature distribution by inserting this temperature contour plot in the solution branch. And yeah, you'll notice that it's 150 everywhere. And that is because we did not actually induce a temperature boundary condition on the external face, right? So you can imagine if this internal face is set to 150, then the entire body will eventually get to 150. So we'll have to actually impose a second condition there on these outer faces, and it's going to be set to room temperature. Yep. So there. Now we have the internal temperature and the external. So now when I solve it, we'll actually get a more interesting result. All right. Now, we want to look at the thermal stresses in addition to all the other stresses, or rather all the stresses that are a result of the structural loads on this thing. So we want to import this this temperature, and actually it does that automatically for us because we already linked the analyses within Workbench, right? If I go back to our project, I'm on these two analysis blocks here. The solution of the thermal analysis is already linked to the static structural, and so we already have this this temperature distribution here. All right. So now, when I solve the static structural, we can look at things like the deformation and also look at the equivalent strain. And I mean, looking at the deformation, because that's kind of the most intuitive thing to look at, it kind of makes sense, right? Like, you know, this end over here is deflecting downward because we have this pipe assembly that's exerting a load in the downward direction. But there's still a uniform, well, you know, there's not a uniform stress around the thing, but there's definitely, this entire body is experiencing some kind of load, right? Actually okay, yes, this is a strain. So this is not, so this deformation is within inches, and this is a strain that was inserted. But actually, I want to look at the stress because that's a little bit more intuitive. to look at. Right. Okay, so now we have a maximum stress of 14,000 PSI. And I actually want to make that a parameter, right? Because right, we want this pipe to survive and be operable. So we'll go ahead and add this maximum stress as a parameter. And then when we go and we do our studies, this will be reported as a parameter. So now I'm going to show you how to essentially set up this design study using the parameters that we made, but I want to take a quick inventory of all the parameters that we've made so far. So we have several parameters in the geometry, right? Most importantly, though, we have the inner and outer diameter of this vertical section and the horizontal section, and we also have the material set as a parameter. And then lastly, we have this maximum stress reported as a parameter too. And so that's really going to be our design criteria. However, you know, the yield stress, or the yield strength rather, of this pipe is going to depend on the material, and the material is changing, right? So we don't want to memorize four different yield stresses and then compare this maximum stress to all those different yield stresses. Really, we just want to know if the pipe is failing or not. So we do have a tool for that here. We'll use this stress tool, max equivalent stress. And within our stress tool, we can insert a safety factor. And when we click on retrieve, we get this plot here. So for this particular plot, you know, structural steel, the most expensive material that we have available, and the thickest configuration of the pipe, you know, it is passing. So we know there's a pipe for us among these that our vendor has given us as options. But I want to report this safety factor for all of our different configurations that we have. All right. Okay. So that's really all the work we have to do in mechanical, right? We've got our geometry as parameters. We've got our material assigned to this body as a parameter, and then we have the safety factor and also the equivalent stress reported as parameters as well. So I can actually just close out mechanical. And then I can go to our parameter set here. Right. And before I do that, I'm actually going to close out of these extra analyses that I'm not using, just to streamline the look. Okay, so now in our parameter set, you know, a whole bunch of information pops up, right? But really what you should be paying attention to is these two windows, this one right here and this one over here. This one on the left is a list of all of our parameters. So, you know, it's good to go through that before you set up your design study. Right, so if we go through that really quickly, we've got our main pipe inner and outer diameters, the vertical pipe protrusion, which we're not going to be using, the vertical pipe inner and outer diameters, and also the half length of the main pipe. You know, the main pipe is this this horizontal section of the pipe. And then for our, well, this is a value of 2. Oh, this was the extra parameter that I added as a demonstration. We actually, yeah, we're not going to be varying that one. And then lastly, we have our material assignment as our last input parameter. And we have all these different options here. And as our output parameters, we have the equivalent stress and the safety factor, like we mentioned before. Okay, and then, so once we've taken inventory of all of our parameters, we can go to this table of design points. So this is really where we're going to be doing our study, is at this table of design points. And so really we want to be working in inches for everything, because that's what all of our problem statement is given in. And really we can delete that, but we don't need it to delete it. We can keep it as it is. And yeah, these are the quantities that we're going to be varying. So if we go to our list of available pipes here. I'm actually just going to make it half the size of the screen here. And we're just going to go through and for structural steel, right, which is our material that we have here, we're going to add inner and outer diameter for the inner for the vertical and horizontal pipe of all these different pipes that we have available. So we started out with the 1/2 inch, right? So because the outer diameter is going to be fixed, right? Because our external geometry is fixed, we're just going to be taking or adding size to this inner diameter of both the the main pipe and the vertical pipe. So actually, let me make this a little bit bigger and zoom in here. And actually got a little cheat sheet for determining this. So let's see, for 2.5, it's going to be 2.125 instead for our next design iteration, because it's going to be 1/8 smaller, right, compared to the 1/2 inch section. So 0.125 is 1/8. And then the next inner diameter is going to be 2.25. And then adding one more, it's going to be 2.375 for the inner diameter. And as I add radius to this inner diameter, the pipe gets thinner and thinner, right? And then let's see. So we've got the 1/2 inch, the 3/8 inch, the 1/4 inch, and then the 3/16 inch. And then going to open up our calculator here and say 2.5 minus 0.125, 2.375. So that's our 1/8 inch. And then we're going to subtract 1/16, which is 0.625. So this inner diameter is 2.4375. Yeah, and you'll notice every time I add a design point, the rest of the columns automatically populate with the previous value. But I've only been adjusting the main pipe, so I also have to do that for the vertical pipe as well, right? So it starts out as 1/2 inch, and then it goes to 3/8 inch. So I can just subtract that here, 1.875. Well, this actually should be, yes, that's correct actually. Well, I'll add it actually to the inner diameter, right? So yes, make it 1/8 inch thicker, so 1.875. And then add 1 more eighth again. Make it 2 inches. And then add 1/16. 2.0625. And then add an eighth or 1/16 again. So now it's at 1/8 inch thick, and then add one more 1/16. 2.1875. Okay. So now we have all of our different pipe thicknesses assigned, and now the pipe goes from its thickest to its thinnest state. And that was a lot of work, right, for this one material. But luckily, if we just Control Shift select all these different rows, we can actually duplicate these design points. So we don't have to do that again, right? Because we don't want to do that again. And we can simply adjust the materials. So now we're going from structural steel. Let's go to our second most expensive material, which is carbon steel. Just starting at this one. And we can duplicate them twice more for the other two materials, copper and once more for aluminum, our cheapest material. All right, so now we've done quite a bit of, we have so many different design cases, right? And we're going, if we were to run this, of course it would take a minute because we have so many different studies to run. So I've already run them ahead of time, and I have them in this PowerPoint here. And it would now be time to make the decision, right? So what was our decision again? Our decision was, well, which pipe are we selecting? And what's it based off of? Well, we're just selecting the cheapest one that meets our design criteria. So if I go to this, this finished list of design points, let me swap views here. We can go to our safety factor column, and right, we don't have a price column, but if we just go to, we know that our aluminum alloy is the cheapest, right? So the thinnest aluminum alloy fails, right? So is there maybe a thinner other component that passes? Like, no, the structural steel thin component doesn't pass. Neither does the carbon steel. Neither does the copper alloy. So really, the second thinnest option here, which should be that 1/8 of an inch, is the only size that passes, and the aluminum is the cheapest material. So therefore, we go to our table, we can make the decision. Okay, well, this 1/8 inch thick aluminum T pipe is actually going to be our best bet. Yep. So that's really all I got for how to set up and how to perform this parametric design study. I hope you guys thought it was a fun exercise and maybe something that you can repeat. You can always go back and watch this video if you need any tips or guidance on that. Are there any questions before we end?
Looks like we don't have any questions quite yet. Let me check YouTube really quick. No questions in YouTube either. So thank you so much, Joel. That was incredibly informative. This will be up on our website, KETIV.com, shortly, as well as on YouTube. Feel free to share it with whoever you'd like. Also contact support@KETIV.com if you have any questions, or reach out to us. We can try to get you into contact with Joel if he's not too busy. I know you're busy, Joel. But yeah, thank you so much for joining us today.
All right, thanks, Tyler, and thanks everyone.
Have a good one.
Yep, you too. Bye-bye.